Assalamualaikum warahmatullahi wabarakatuh, Doctor. My name is Muhammad Arshath bin Muhammad Saleem. My fellow team members, Fadhil, Raihan, Gunawan, Reza, Mouna, Hendrian, and also Mohamed, Gibran, Dzikry from group DeadlineZero will be presenting about our UC system, which is the Smart Irrigation Solution. So firstly, let's talk about what is Smart Irrigation Solution. So Smart Irrigation Solution is an IoT-based mobile application that is designed to automate and also optimize watering in agriculture through environmental sensing and also real-time weather integration. So the main problem that leads to this solution is actually the traditional irrigation use fixed schedules and also manual labor. So both of these ignore real-time soil moisture, temperature, and also rainfall. So for an easy example, let's say an old traditional irrigation has an fixed schedule for every morning at 8 o'clock, it will water the plant. So no matter whether it is raining or not, the temperature is low or high, the soil is humid or not, it will plant the water. It will water the plants no matter what. So if it's raining, the plants usually will have sufficient water for an efficient growth rate. But the old system, the traditional irrigation will still water the plants. So it will waste water and also can kill the plants because of the excessive water intake. So let's look at the statistic or numbers to understand more. So 70% of global fresh water is consumed by agriculture. So that's a lot of water to be wasted just because of this silly fixed schedules issue. And also the agricultural workforce is has declined from 44% to 26% from 1991 until 2023. So it shows that we are in demand of automation because of the low number of labor workforce in agricultural sector. And finally, it is proven that IoT-based irrigation can reduce water waste by up to 45%. So let's move on to the target users and also the context of use of our system. Mainly, we have three target users: home gardeners, small-scale farmers, and also system admins. The home gardeners, they seek precise and also automated watering without manual monitoring. The small scale farmers, especially the Southeast Asian farmers, they need irrigation automation to compensate for their low number of labor workforce. And lastly, system admins, they will manage user accounts, IoT device registration, plan profiles, and also system logs. This is usually for all the systems. So moving on, let's look at why this is a UC system. Why Smart Irrigation Solution is a UC system. So firstly, the system has context awareness. It uses soil moisture sensor, YL69, and also open weather API to drive autonomous irrigation decisions. So the users doesn't need to input any data for as an input for the system. The system will retrieve the data from the sensors and integrate with the open weather API to make autonomous decision. So it is aware of the context and also it has embedded computation. It has ESP32, a microcontroller that integrates into the physical plant environment to detect the soil moisture, the temperature, and so on. And furthermore, it also has implicit interaction. So implicit interaction, the water pump activates or deactivates without the user command. So the user just need to supervise whether it is working correctly through their mobile app, and they doesn't need to operate. They don't need to turn on and turn off the water pump. And lastly, this is the most important for our system is mobility. It uses Flutter mobile app that allows remote monitoring control remote monitoring and control from any location, from anywhere. So this is the justification of why smart irrigation solution is an UC system. And moving on to the next person.
So my name is Reza Hendrian, and I will present about UC characteristics of the system, and then the HCI classification of the system, then the requirements, both functional and non-functional, and as well as the interaction analysis. So the first UC characteristic of the system is context awareness. So the system continuously monitors contextual data such as soil moisture levels and real-time weather conditions to make intelligent irrigation decisions. So if, for example, the weather condition is cloudy or it's raining, then the system will pause the irrigation. And this demonstrates that the system is able to adapt to environmental context without the user explicitly telling it to do so. The second one is distributed system. So the architecture spans multiple distributed components. The first one is the edge IoT devices, those ESP32 sensors that they put on the plant level. The second one is the cloud backend, which uses Firebase. The third one is the external API, which uses Open Weather API for retrieving the weather condition at the location. And lastly, the mobile client application, which uses Flutter. And all these components communicate asynchronously over Wi-Fi and the internet. The third UC characteristic is implicit ACI. So the core irrigation logic of the system works without requiring any kind of user input. So the system is able to autonomously decide when it wants to activate or deactivate the water pump based on sensor readings and weather data. In this case, the users are only notified when their intervention is required. For example, when the moisture is too low or a device disconnects, and this minimizes unnecessary interactions. The last UC characteristic is autonomy and artificial intelligence. So the system uses a rule-based autonomous decision making, such as comparing real-time sensor data against specific thresholds and weather conditions. And this form of embedded intelligence enables it to act on behalf of the user without constant supervision. The next one is the HCI classification of the system. So we have two here. The first one is EHCI, and this is from the mobile app component of the system because from there the user needs to initiate the configuration and they also need to monitor the system. And the second one is IHCI or implicit human computer interaction. And this is for the accompanied smart devices of the system, such as the IoT sensors that they plant at the plant level. Now, for the requirements, there are seven functional requirements here. First one is automatic irrigation. Second one is real-time monitoring. Third one is weather integration. Fourth one is device management. Fifth one is plant specific threshold. Sixth one is notification alert, and the seventh one is reporting. And this is the non-functional requirements. So notice here that the performance, the the response to user actions needs to be within 2 to 3 seconds, and the sensor data is updated every 5 seconds. And this is pretty much demonstrates the entire point of uh, embedded computing. Like the system needs to be able to respond very quickly. And there's also a usability non-functional requirements here, which is an intuitive interface accessible to users. And this is the one that we attempted to solve in our prototype. And of course, security, there's Firebase authentication. And the next one is reliability, which requires a stable connection with active internet connection. And last one is mobility because the system uses a mobile app, so it can be accessed from any location, and the IoT devices operate independently. Now, the next one is interaction analysis. So, for the humans, the system targets home gardeners, and it aims to alleviate the physical labor and guesswork based on a traditional fixed schedule watering. And this is helpful to them because it transforms their experience from a very taxing manual chore to more of like a supervisory role. And this grants them a peace of mind and convenience because they can just remotely monitor from their application, and that's very handy. The second one is with the physical world, and these are the elements that the system measures and manipulates. For example, the soil moisture level, or the weather conditions. And the third one is computer or ICT, and this is the digital ecosystem where data processing and storage occur. And again, this relies on that distributed architecture that I already explained earlier. And that's it for my part.
For the human-computer interaction evaluation based on aquarium, I will be taking over. So aquarium is used to evaluate the quality of human-computer interaction in ubiquitous computing system. In our evaluation, we focus on five characteristics: context awareness, mobility, transparency, attention, and calmness. First is the context awareness. The system performs strongly. This is because it does not only depend only on fixed watering schedules. Instead, it uses real-time soil moisture data, live weather information, and plant-specific threshold to decide whether irrigation is needed. For example, if the soil is dry but the system but the weather forecast shows rain or cloudy condition, the system can pause the irrigation. This shows that the system responds to the actual environment and not only the manual user input. The second, it is the mobility. It is also strong. User can monitor soil moisture, control irrigation, manage plant profiles, and view reports through the Flutter mobile application. The system also supports BLE pairing for device registration and Wi-Fi for ongoing cloud data transmission. This means users do not need to be physically near the plant all the time, which is improve convenience, especially for home gardeners. However, the other three characteristics are evaluated as moderate. For transparency, the system provides a dashboard, reports and logs and device status so user can see what is happening. But the weakness is that the system does not clearly explain why the pump turns on or off. For example, the app should clearly show message like pump activated because soil moisture is below threshold or irrigation paused due to rainy weather. For attention, the system sends useful notification for low moisture, device disconnection, and uh, irrigation activity. This helps user respond quickly. However, the report does not clearly explain whether the notifications are prioritized or customizable. Without this, the user may receive too many alerts and start ignoring them. Lastly, for calmness, the system reduces manual watering because irrigation is automated. The deep sleep mode also allows the IoT device to work quietly in the background. However, setup steps such as pairing, Wi-Fi inputs, plan selection, and internet dependency may still create interruption or frustration for users. Overall, the system has a good human-computer interaction foundation, especially in the context awareness and mobility, but it can still be improved by making system decision more explainable, reducing notification overload, and simplifying the interaction flow for non-technical users.
Hello, my name is Fadhil Raihan Gunawan, and I'm going to be presenting our improved prototype for the chosen current system or our chosen research. We will going to start with the login page, which we use the same auth option as the original, which is the email and Google sign in, but with a calm, green design and personal greeting set as the relaxed tone which supports the calmness. And then we go to the main dashboard, which fixes the original system's biggest gap. We added a why is the pump off card that explains every automatic decisions in plain words. So like soil level, weather, and also the time since last watering. This directly addresses the transparency. Users can also adjust the threshold view with the threshold slider and the reason updates instantly, so they see the effect before they pump the runs. The run test cycle button lets them check the system is working anytime. So in here in the activity page, we it shows that every pump event with the reason behind it. For example, soil drop to 26% below threshold of 41%. Users can scroll back and check why each watering happened, which strengthens the transparency. And then the top stats summarizes the irrigations, water saved, and also the rain past events. And then here we have the plant page. So on the plant page, switching plant profiles auto sets the right moisture threshold for the plant, spinach, lettuce, cucumber, or rose. Users can switch with a single tap, no manual reconfiguring. This supports the context awareness aquarium. And then here is the device page plus the offline page. The device page shows all the device info in one place. So it shows the plan, threshold, last reading, and firmware of the specific devices. So users don't jump between screens. And then when the internet drops, the app falls back to Bluetooth, so the pump still works, addressing mobility. Here, as you can see in the right side. The amber banner shows offline as a normal mode rather than an error, supporting the aquarium of calmness. So here is the devices setup pages, which follows the 4-step onboarding wizard. So this set, as you can see here, is we have a stage of power on, pair, pick a plant, and then done. So it's like a clear progress at every step, which shows the calmness. And then picking the plant auto sets the threshold, so no manual setup, which supports the context awareness aquarium. So lastly, here are the other pages, which includes the profile, settings, and also the notification pages. So alerts are split into critical, important, and info. So there's no notification overload, which supports attention aquarium. And then we have quiet hours post non-urgent alerts at night. So we can actually post any alerts during at night, as you can see here, which supports calmness. And then we have the SMS backup delivers critical alerts even with no internet. If let's say there's no internet during that time, it can be sent notification can be sent to through the SMS, so, which supports the mobility. So that is all from us. Thank you for watching.